Okay, the new homework sets, well, it's not homework, problem sets for you to get ready. By the way, the exam will be either on the Wednesday that is just before the spring break or on the Wednesday just after the spring break. The dates were on the syllabus. I think one is the 6th of April. The other one is the, which? 18th of April. Which one did we prefer? Did we decide on that? Did I ask you this question before? No, I guess not. Which one do you want? The exam will be most likely an in-class exam, closed books and notes, and you should be getting ready by the exam date, of course. So, two possible dates, either the 6th or the 18th. Between the 2 days, you've got the spring break. So if you want to use your spring break to get ready for the exam, of course, then we do it on the 18th. If you wish to just use the spring break for leisurely time, then we do it on the 6th. Which one do you want? Huh?
After the break.
After the break. How many people prefer to have it after the break? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many people prefer to have it before the break? You're the minority. Only one person. Why do you want it on before the break? Huh?
I don't want to study in break.
Well, then you study before the break, and then just don't forget anything during the break. Okay? We'll have it on date. Okay, we'll have it on the 18th. The exam will be normally in class, closed books, notes, at least 2 hours or possibly more. Sometimes 2.5 hours. But you never know. I may also add a take-home part to it. Traditionally, I don't do that, but nevertheless, I may do it this time, okay? Because we have only 2 exams, the midterm and the final. And since we don't have any homework, well, we do have the problem sets, but we're not grading the homeworks. So I may have to ask a little bit more in the exam than I typically do. Okay? How are you going with the problem sets? Are you doing okay? Are you working on them? Or are you just taking time off and just come here to listen to what the teaching assistant solves for you? Which one are you doing? No answer. Probably you're doing the second one, I guess. Huh? Okay. You should be working on the problem sets. Did we finish up the dictionary form? We didn't. We started on it, I remember, but we did not finish it. So let's just begin with the example problem. In the dictionary form, we had the problem of maximizing x1 plus 3x2, x1 plus x2 plus x3, which is a slack variable, equals 6, and minus x1 plus 2x2 plus x4, which is again a slack variable, equals 8. And x1, x2, x3, x4 greater than or equal to 0. And we typically work with the equality portion, and we throw this also into the constraints in the form of row 0. We append an additional variable z, which equals x1 plus 3x2. And when you do that, the problem becomes the maximization of z, the additional variable, where z is defined by the objective function, That's your row 0. And then you simply write down the other equations at the bottom. And then proceed with this part, keeping in mind that everything must be non-negative other than z. Z can be anything. Okay? Z is unrestricted because the objective values could be anything. All right. So the initial solution we began with, the initial basic feasible solution we began with, since I've added also one additional row here, I'm going to have 3 basic variables rather than 2 coming from the lower part of the box, and 1 coming from row 0. Row 0 always supplies 1 basic variable, which is z. Okay? And so we begin with a z value of 0, x3 value of 6, x4 equals 8. These are the basic variables. These are the true basic variables, so to speak. You know, row 0 is sort of artificially added. So these are the basic variables. And the remaining variables are non-basic. x1 and x2 are non-basic. Okay. How do I know the values of x3 and x4? Well, when x1 and x2 are 0, the equations tell you what the values ought to be. Okay? All right. So we begin with this solution. And to be able to proceed to see if there's anything, if there's a adjacent basic feasible solution or an adjacent extreme point which gives you a better objective value, that's the way the simplex method goes, we actually wrote down the set of equations we have in the box in the following form. We kept the basic variables on the left, and we took everything else to the right side, which gave us 0 plus x1 plus 3x2 for the first, or row 0. Then x3 equals 6 minus x1 minus x2, and 8, x4 equals 8 minus, or plus x1 rather, minus 2x2. Okay? That's the dictionary form, with basic variables on the left, everything else on the right. And of course, in the dictionary form, it's nothing different from the equation form. It's the same thing. In this form, of course, when the non-basic variables are set equal to 0, you immediately read off the solution. Z equals 0, x3 equals 6, x4 equals 8. That's the basic idea here. And now you ask yourself, well, can I improve this by exchanging the role of some basic variable with a non-basic variable? That was the question. And to answer that, first you investigated the rate of change in z as a function of the non-basic variables, one at a time. So the rate of change in z will be 1, the partial derivative, coefficient 1 here. And the rate of change for relative to x2 is equal to 3. As long as this is a maximization problem, right? Yeah, this is a maximization problem. So as long as there's a non-basic variable whose rate of change is positive, you want to be able to enter that, because that gives you an increase in z per unit increase in whatever you decide to enter. In this case, you've got 2 choices. One of them gives you 1 unit increase in objective function value per unit increase in the candidate. The other one gives you 3 per unit increase. And traditionally, people choose the most positive one, so we select the second one, which means we enter x 2. Enter means make it basic, allow it to become positive. But then somebody else, or one of the basic variables, should become negative. And to answer that, so we increase x2 as much as possible. Sometimes to plus infinity if that's allowed, okay? To see how much you can increase, you need to investigate the blocking of, or what blocks the increase in x2. You know, something will limit that. And to do so, you investigate these equations, 1a, 1b, 1c. Let's just name them like that. In this case, x2 will be non-negative, will be increased, but x1 is still non-basic, which means it's still 0. Okay? For that reason, I just ignore x1. It will be still 0. And so 1b and 1c tells me that x3 is equal to 6 minus x2, and x4 equals 8 minus 2x2. So as you increase x2, of course, x3 and x4 both start going down from their current values. And to ensure that they both stay non-negative, you just impose this. And of course, that tells you that x2 is at most 6 from the first one, or x2 is at most 4 from the second one. This is called the ratio test of the simplex method, if you know have been exposed to the simplex method before. So this is the ratio test. These are the ratios we are looking at. This is the ratio of 6 to 1, the constant to the value, negative of the value here, which is, of course, positive if you think of that on the left side. Again, this is also the second ratio. Which one is the determining or the blocking variable? The smallest of them is the blocking one. Because as soon as you increase x2 to the value 4, x4 becomes 0, the other one becomes 2. Any further increase in x2 will make x4 a negative number. Okay? You do not want that. All right, so blocking occurs at x2 equals 4. The new solution with x2 equals 4, x1 still equal to 0 will be x3 will be equal to 6 minus x2, which is, of course, 6 minus 4, 2. x4 equals 8 minus 2 times x2, which gives you 8 minus 8, 0. Okay? So, because of this 0 here, x4 becomes non-basic. So, you know who to enter. x2 enters, and you know which one will be exiting. So x4 leaves or exits out of the current set of basic variables. I think we proceeded up to this point. I'm not sure if we did anything after this. Did we do anything after this? Maybe we did. Well, let's just proceed. So what we do is, with this information, we try to make the system of equations look like the same form that we started out with. Okay? In other words, we want to have the basic variables on the left side with coefficients of 1. Each one should be appearing exactly once per equation, or in one equation. And all the remaining variables, the non-basic variables, should be on the right side. Okay? And to do that, we begin with 1c. Why 1c? Because 1c is the equation which swaps the rows of the incoming variable and the outgoing variable. x2 is the incoming variable, x4 is the outgoing or the exiting variable. That's the only equation where they both show up. Okay? And solve for x2. So when you do that, you obtain one equation for the newcomer x2 basic variable. And that's going to be how much? When you solve for that, 2x2 will be, well, it will be 1/2 times 8 plus x1 minus x4. And then you divide by 1/2 and everything will be okay. Okay? For those of you who might have seen the simplex method before, this is what we're doing here is equivalent to the pivoting operations, okay, if you've been exposed to that. Anyway, this is simply solving for x2. And then substitute this expression for x2 in 1a, the remaining equations, and 1b. Okay? So wherever you see x2, you just substitute for that. So this is, of course, 1c prime now, so to speak, the new version of 1c. And 1a prime is obtained by, well, what was it? It used to be z equals 0 plus x1 plus 3x2. Instead of x2, I'm going to write down the new expression for that, 1/2 times 8, which is going to be 4, then plus 1/2 x1 minus 1/2 x4. So what is the output of this? This is going to give you 12. That's the constant. And then you've got x1 and 1/2, 3/2 x1, which gives you 5/2 x1. And then what else? That's it. Minus 3/2 x4. That's your right-hand side for the first, or equation 1a prime. Okay? 1b prime is similar. x3 equals 6 minus x1 minus x2. So minus x2 will be 4 plus 1/2 x1 minus 1/2 x4, which gives you, I don't know, 6 minus 4 equals 2. Minus x1 minus 1/2 x1, that's minus 3 over 2 x1. What else do we have? Plus 1/2 x4. If I did not make a computational mistake, this is what you've got. So, the new system looks like the following. Okay, that's your new system in dictionary form. Then you inspect the rate of change for z relative to x1, the non-basic variables. That one gives you 5 halves per unit change. The second one gives you minus 3/2. This is bad. Anything increase, well, if you increase x4, you force your z to go down from its current value. What's the current solution, by the way? Well, the objective value is z equals 12. x3 and x2, they are 2 and 4. And the non-basic variables, x1 and x4, they are 0. Basic, non-basic. Okay? And of course, you get that by simply taking x1 and x4 equal to 0, and it tells you what the solution is. Again, recall that non-basic variables correspond to those non-negativity constraints that are taken to be active. Okay? You're just choosing these to be active constraints. And that's why, you end up with this solution. All right. So since there's only one positive rate of change here, and we're maximizing, we enter x1. Okay? And again, we look for the blocking variable. In that case, we inspect x3 and x2 as a function of the entering guy. x3 equals 2 minus 3/2 x1. The other one is 4 plus 1/2 x1. When x1 is increased, you want that and this to be non-negative. When x1 is increased, of course, this is going down. So this tells you that x1 is at most how much? Two divided by 3/2. How much is that? 4/3? Yeah. The other one does not block you in any way because as x1 is increasing, 4 plus a positive number will never go down. Okay? So if you've got a plus number here, a plus coefficient for the entering variable, you don't need to look at that. No need for this. No need to look at a ratio for that. All right, so x1 blocks and x1 is the leaving variable. It's the one which is basic now. I'm sorry, not x3 is the leaving variable. Because x1, when it becomes 4/3, x3 will become 0. Okay? All right. Update. You tell me what to do now. Which equation do I take? 1b prime, yes. 1b prime. And I swap the roles of x1 and x3. So you solve for x1, which gives you 2/3, 1/3/2 times, what is that? 2 plus 1/2 x4 minus x3. So let me write minus x3 first. Which, upon simplification, will give you what? 4/3 minus 2/3 x3, and then plus 1/3 x4. Okay? And then you substitute this x1 value in one A prime and one C prime. And when you do that, you get the following. Let me just make sure that I've got the right information here. It seems okay. x2 equals, where am I? Wait a minute. Okay, sorry. So 1A prime refers to z. So z equals 46/3 minus 5/3 x3 minus 2/3 x4. And 1C prime gives you x2, which gives you 14/3 minus 1/3 x3 minus 1/3 x4. Can we open a window? It's too hot here. Okay, so when you update it, you obtain these equations. And let me write it here in orderly fashion. Z equals 46/3 minus 5/3 x3 minus 2/3 x4. And x1 equals 4/3 minus 2/3 x3 plus 1/3 x4. And x2 equals 14/3 minus 1/3 x3 and minus 1/3 x4. One A double prime, one B double prime, one C double prime. I just noticed that this is a poor choice of numbering. I should have numbered these, rather than primes, 2A, 2B, 2C, etc. But nevertheless, this is what we did. Okay? Yes?
Can you once more explain why x3 exits there is no
Why x3 exits? Okay. We're trying to make x1 as large as we are permitted. And when you make x1 from this non-negativity for x3, if you solve for x1, you get x1 becoming at most 4/3. Okay? Take this, etc. You know how to do that. So when x1 becomes 4/3, you will get 0 for x3 here, which means that x1 will be at most 4/3. It will be the new basic variable, but x3 exits in that case because it becomes 0. Does that answer the question?
Why x2 doesn't exit?
Or why you don't care about this? Is that what you're asking? Well, the reason is x2 is defined by 4 plus 1/2 x1 because this is a positive coefficient in front of the newcomer. Increasing x1 will not cause x2 to go down. It will always go up. So there's no danger of x2 ever becoming 0. Okay? So it will continue to stay as basic. It cannot leave. Any other questions? All right. At this point, you again inspect the change in z as a function of x3 and x4, you look at the partials, and you see that they are both negative. So relative to x3, you've got minus 5/3. Relative to x4, you've got minus 2/3. So making any of these non-basic variables a basic one does not give you any gain in the objective function value. So at this point, you stop. Nothing, no exchange of basic and non-basic variable will give you a better objective value than you currently have. Currently, your objective values are 46/3, etc. This is the solution. So at this point, you can stop. Optimal basic feasible solution is directly available in the system you've got here. x1, x2 are the basic variables, x3, x4 are the non-basic variables. And so your solution is 0, 0 for the last two components. x1 is 4/3, and x2 is 14/3. And the corresponding objective function value is 46/3. That's the basic feasible solution on hand. Okay? The feasible region of this problem in 2 dimensions in x1, x2 plane gives you 4 constraints, the original problem without the slacks x3 and x4. And it looks something like this. On this one, x1 is equal to 0 on this line. Okay. On this line, x2 is equal to 0. Which line is this? Anybody? From the original problem, if x3 and x4 are removed, you've got the original problem in less than or equal to form. x3 equals 0? Could be. Let me check though, because I forgot what the constraints were. Huh?
This was the last one, is it?
Look at the original problem. Don't look there. That's a different description. We just manipulated systems of equations. We dressed them in different clothing each time we did that. But it's the set of solutions never changes. Okay? It's the same polyhedral set all the time. The original one, the first constraint was x1 plus x2 less than or equal to 6. So this is that constraint. And the associated slack variable is x3. So when x3 is equal to 0, you're on top of that hyperplane. And this one corresponds to x4 equals 0. Okay? So you began here, which is the origin. x1 is 0, x2 is 0. That was the initial basic feasible solution in x1, x2. Of course, if you complete this to x3, x4, what do you get? You get whatever the solution told you. You should be getting that. Okay? All right. Then we moved here, I think. Or maybe this one. Which one did we move to? What is the second solution? What was it? x1 equals 0, x2 equals 4. That's the one that we moved to, which is x1 equals 0, x2 equals 4. It is this point. And then from here, so we moved here from the origin to this neighbor, and then we moved here, which is this. This is the point 4/3, 14/3. Okay? You can always compute your slacks, x3 and x4, by simply taking the right side minus left side of the constraints, the original two constraints. Okay? And that computation should give you the same values that we obtained in these solutions in the dictionary form. All right. The dictionary form is originally, I'm not sure who devised it, but Hvatal is the originator as far as I know. Maybe not. But he's the promoter of this, okay? Hvatal has a book on linear programming, and he gives a full description of the dictionary form, which I gave you the basics of in the lecture. And according to him, plus his students, apparently that's found very natural by many people. I don't know if you found it natural or not. To me, it's quite natural, too. You just take the system of equations, express the basic variables in terms of the non-basic variables, and then you substitute as necessary to always make your system look in that particular format. Okay? And then that tells you how to proceed until the termination. How many people found that natural? Let me just see your hands. Okay, at least some people. How many people found it quite complicated? No answer. Okay. Good thing that the camera does not capture you during that answer. All right. Anyway, maybe it's the way I present it. Apparently, it's found quite natural by Hvatal's students. Most books, as well as most instructors of linear programming, use the tabular form. Tabular form is nothing but the equation form, except that the variables are removed. So in the table, you just see the coefficients of the variables, but not the equations themselves. So let me just give you the correspondence. Let's just make a table here. In the dictionary form, you've got the initial solution, z equals x1 plus 3x2, x3 equals 6 minus x1 minus x2, and x4 equals 8 plus x1 minus 2x2. That's the first solution. In the equation form, you have exactly the same thing, except that all the variables are on the left side, all the constants are on the right side. So That's what you would see as your initial solution. With x1, x2 being non-basic, the solution is immediate. Z equals 0, x3 equals 6, x4 equals 8. Okay? In the tabular form, you get even more lazy by you use simply the coefficients of the variables and define a tableau here. Each row and each column associated with a variable. And the basic variables are z, x3, and x4. You just list them here. These are the basic ones. These are the non-basic ones. Of course, in the dictionary form, you know what the basic ones are because they are on the left. In this one, you have to somehow keep track of what's going on. In this one, you have to do the same thing. You just enter the coefficients, 1, 0, 0. Because z has a coefficient of 1 here, 0, 0 in the remaining equations, okay? x1 has a coefficient of minus 1, 1 and minus 1. x2 again minus 3, 1, 2, 0, 1, 0, 0, 0, 1. And then what do we have? 0, 6, 8. These are the basic variables. These are the non-basic variables. Well, the basic variables are listed here, and of course, because of the location or the position of 1, you exactly know that x3 appears in this equation with 1 here. x4 appears here with 1 here. So each basic variable is associated with exactly one equation, okay? Even though the variables and equations have nothing to do with each other. When you suppress the non-basic variables, they have something to do with each other. Each one goes in a one-to-one correspondence. Okay. So in the tabular form or in the equation form, you decide who to enter by simply inspecting, as in the case of the dictionary form, the rate of change in z. Except in the dictionary form, the non-basic variables are on the right side. So when you put them on the left side, of course, you're looking at the negative of the rate of change. So for that reason, this minus 1, or that minus 1, tells you that the rate of change in x1, in z, sorry, as a function of x1 is the negative of that, which is plus 1, okay? So that can be entered. x2 gives you 3 units of increase in z per unit change in x2, upwards, of course. So you decide to enter x3, and you indicate x2, sorry. And that's how you indicate that, okay? So we're using the same information. Del z over del x2 is equal to the negative of what you see in row 0. That's it. For that reason, you enter the most negative coefficient in row 0, or the variable associated with the most negative coefficient in row 0. And then what do? You impose non-negativity. How do you impose that? Over here, how do we impose that? We look at the same equations. x1 will still be 0. I'm doing the same iterations that we did before, but with a little bit different flavor. So enter x2 first of all, and then to identify the blocking variable or the exiting variable, you inspect the equations, which tells you that x2 plus x3 is equal to 6. x1 is still 0. And then 2x2 plus x4 is equal to 8. Since you impose x3 and x4 to be non-negative, or you want that, okay, that tells you that x2 can be at most 6, and x4 can, not x2, sorry, yeah, x2 can be at most 4 from the second one. So that is indicated by the ratio test of 6 to 1, which is the current right-hand side, to the positive coefficient here, the ratio of 6 to 1. The other one is 8 to 2, that ratio. Whichever one is smallest, that's the one that tells you when the blocking occurs. So blocking occurs with x2 becoming 4, in which case x4 is the non-basic variable in the new system. Okay, so that's why x4 exits. That's why you indicate that by this little arrow. At least I typically use these little arrows. Some people may be using something else. And then you pivot on that circled element to transform this description of the problem into a new form corresponding to the new set of basic variables. So when you pivot, how do you pivot? What you want to do is you want to create a 1 here as a coefficient, 0 and 0 in the remaining equations. And you can do that by elementary row operations. First, so that's called the pivot element. And the row occupied by the pivot element is called the pivot row. And the column occupied by the pivot element is called the pivot column. The pivot row, the new pivot row, is simply 1 over the coefficient you see here, pivot element, 1 over the pivot element times the old pivot row, or the current pivot row. So you divide everything in this row by 2. Biraz sessiz olur musunuz arkadaşlar? Okay, you divide by 2 the row associated with x4, and then you add, so that creates a 1 here, so you add 3 times the new version of this row to the top row, so that 3 times 1 and minus 3, they cancel and create a 0. Okay? You do the same thing here. You have a 1 here in the new version. So 1 times, minus 1 times, that will cancel with this one, so it will create a 0. So for other rows, say row I, or the new row I, equals the old row I plus negative of the coefficient in row I of pivot column times the new pivot row. And I have no space left here, so new pivot row. I don't know if the camera can see that. Okay. Okay? So when you update that, you should get the corresponding version of the tabular form. So what is the second solution? Well, let's take a 10-minute break, and then maybe we'll do it after the break.